Welcome to this explainer. Today, we're going to unravel the incredibly fascinating, highly precise world of plastic injection molding. We're taking a complete chronological journey to understand exactly how a perfect plastic part is actually crafted. We'll trace the whole process, from the very beginning of selecting the raw chemical ingredients right through to applying advanced digital optimization and simulation. Whether your goal is knowing how to select suitable materials, or analyzing and calculating process parameters, or you just want to understand how to apply cutting-edge simulation to optimize those parameters, you are absolutely in the right place. Let's get into it.
To make this complex journey easy to digest, here is our agenda. Section 1. Selecting the ideal materials. Section 2. Mastering injection process parameters. Section 3. Rapid tooling and cooling. And finally, Section 4. Simulation and process optimization.
Section 1. Selecting the ideal materials. Okay, let's dive into this. The absolute foundational step that dictates the success of your entire manufacturing process is knowing how to select suitable materials. Honestly, before you even turn on a machine, your polymer choice completely locks in your processing range, your thermal properties, and the final part's mechanical strength. What's really fascinating to consider is how the two main classes of thermoplastics, amorphous and semi-crystalline polymers, behave differently under heat. Think about the molecular reorganization during the cooling phase. Amorphous polymers have this random and tangled molecular structure that simply slows down and thickens up as it cools. Semi-crystalline polymers, on the other hand, actually fold into highly organized, dense crystalline regions as the temperature drops. And this structural difference isn't just a fun piece of trivia. It directly affects the degree of crystallinity, which in turn dictates the dimensional quality, the shrinkage, and the warpage of your final produced part.
To put this into practice, you have to precisely match your material to the product's required mechanical and aesthetic properties. Take amorphous materials like acrylonitrile butadiene styrene, or ABS, and polycarbonate. ABS is fantastic for items requiring a really great surface finish and dimensional stability. Think about the sleek outer casing of a cosmetic compact. Then you have semi-crystalline materials like polypropylene, or PP, and polyamide. Polypropylene is highly resistant to chemicals and moisture, making it the absolute go-to choice for food storage packaging that needs to withstand, say, hot water washing. Ultimately, the material you select completely dictates the processing parameters we need to calculate next.
Section 2. Mastering injection process parameters. That brings us perfectly into our next phase. Once you have your ideal plastic, you really must master the machine's operating conditions. Analyzing and calculating the parameters in the injection molding process is where the real engineering magic happens.
The injection molding cycle itself operates in 5 strict chronological steps. First up is plasticating, where the material is melted down. Second is filling, where that molten plastic is aggressively pushed into the mold cavity. Third is packing, where extra pressure is applied to compensate for the plastic shrinking as it cools. Fourth is the cooling phase, where the part solidifies. And finally, ejection. Understanding the delicate interplay between polymer flow dynamics and thermal profiles during these 5 phases is absolutely crucial, because poor control during any of these steps is exactly what causes defects like shrinkage, warpage, and residual internal stresses that will just ruin your product quality. So the really crucial point here is mastering your thermal profiles, specifically melt temperature and mold temperature. Melt temperature directly controls the viscosity and flow behavior of the polymer. If it's too high, the material just degrades, but if it's too low, it simply won't fill the mold. Mold temperature, on the other hand, conditions the entire cooling rate. Elevated mold temperatures are great because they really enhance the surface finish of the part, but there's a major trade-off. They extend your cycle durations. Lower temperatures will speed up your production but massively increase the risk of warpage.
But it's not just about temperature. You have to carefully calculate and analyze mechanical parameters to serve as your defense mechanisms against product degradation. Injection speed must be optimized to ensure uniform filling without trapping air or causing material shear. Packing pressure is huge. It literally packs more material into the mold to prevent voids and sink marks as the plastic cools and inevitably shrinks. And finally, the ejection temperature just has to be right. If you eject the part while it's too hot, it loses its dimensional stability and will warp the second it leaves the mold.
Section 3. Rapid tooling and cooling. Now that we've got our machine parameters dialed in, let's shift our focus to the physical molds themselves. The actual metal or printed tool you inject the plastic into is a massive determining factor in your production efficiency and part quality. I really want you to let this number sink in. 50 to 80%. Literally 50 to 80% of the entire injection molding cycle time is dedicated purely to the cooling phase. That means if you want to optimize your process, save serious money, and reduce energy usage, the cooling phase is absolutely your primary target.
Thermal imaging of a mold brilliantly illustrates exactly why cooling is such a massive challenge. Right after opening, the parts in the mold cavity inserts can easily hit around 100 degrees Celsius. Heat management is completely non-negotiable here. If you don't extract this heat efficiently before closing the mold for the next cycle, your parts will deform and your production line will just crawl to a halt. Efficient cooling channels are essential to rapidly dissipate this intense thermal energy.
Historically, to handle these kinds of temperatures, molds were made out of hard steel. But steel molds take months to machine and can cost tens of thousands of dollars. Enter rapid tooling. Using additive manufacturing technologies like fused filament fabrication, stereolithography, and multi-jet fusion, engineers can now actually 3D print mold inserts out of specialized polymers in just a matter of hours. This allows for incredibly fast, low-volume prototyping of complex items, like those cosmetic compacts we mentioned earlier, so designers can test physical parts before ever investing in an expensive hard steel mold. But soft tooling definitely isn't perfect. Because these rapid molds are printed from polymers, they have incredibly low heat conductivity compared to steel, which drastically extends that cooling time we just talked about. They also introduce some unique defects. For example, rougher 3D printed surfaces can cause the plastic part to stick during ejection. Engineers have to be clever and adjust their parameters to solve this. Things like lowering the part temperature before demolding, applying release agents, and reducing the ejection speed. Furthermore, even when printed at 100% infill, some printed molds can suffer from void collapse under high injection pressures, which then directly replicates as a defect on your final part.
Section 4, Simulation and Process Optimization. Which leads us to a pretty critical question. With all these complex variables, from molecular structures and thermal profiles to rapid tooling challenges, how in the world can we predict and fix physical issues before we ever melt a single drop of plastic? Well, the answer lies in applying simulation to optimize the parameters of the injection molding process. As the source material bluntly points out, classical trial and error or single objective approaches are insufficient to explore this design space. Guesswork on the factory floor is officially dead. The sheer number of conflicting targets, like wanting a lightning-fast cycle time but also needing perfect temperature uniformity to prevent warpage, makes it literally impossible for a human to calculate manually. Today, engineers must rely on advanced simulation software like Moldic 3D and Autodesk Moldflow to visualize polymer flow dynamics and thermal behavior in a completely virtual environment.
Let's see how this builds into true optimization. The software doesn't just show you what will happen, it uses advanced computational algorithms to find the perfect settings for you. We're talking about evolutionary algorithms that literally mimic natural selection to globally optimize parameters, alongside simulated annealing and particle swarm optimization. But what's truly incredible is the use of multi-objective optimization. This allows engineers to simultaneously improve conflicting goals. For instance, calculating how to reduce cycle time to lower energy usage while concurrently minimizing defects to reduce plastic waste, making the entire manufacturing process far more sustainable. There is a bit of a catch, though. Running hundreds of full, high-fidelity 3D simulations to let these algorithms find the best answer takes massive amounts of computing power and time. To solve this bottleneck, researchers use surrogate models. By utilizing advanced mathematical techniques like kriging, response surface methodology, and artificial neural networks, these surrogate models act as incredibly fast digital shortcuts. They mimic the heavy 3D simulation, allowing the optimization algorithms to evaluate thousands of parameter combinations in a fraction of the time, drastically reducing computational costs. We've covered a lot of ground today, from selecting the exact right molecular structure of a plastic, right through mastering injection parameters, exploring 3D printed rapid tooling, and applying advanced simulations. But the manufacturing world never stops evolving. As we look to the future, the integration of real-time sensor data with these optimization algorithms points to a deeply fascinating frontier. Can adaptive machine learning and AI completely take over, adjusting and optimizing mold parameters in real time as the machine is literally running? It's a provocative thought for sure, and one that promises to make smart manufacturing even more efficient, sustainable, and perfect. Thank you for joining me in this explainer. Keep analyzing, keep optimizing, and stay curious.